Okay, so how is everyone today? Good, I hope. All right. So then, so there's been a homework glitch. So if everything, if there were no flaws, why is this not turned on? Oh, there it is. If everything was operating completely smooth, then we'd have homework due on Friday. But there's not, right? I don't think it's there. So we're not going to have anything to turn in on Friday because it wouldn't work at all for me to just suddenly say, oh, you have to do this with such a short turnaround. So sorry for that. What we'll do is we'll shift them so that they're due next week, and we'll keep marching on. All right. So when we left last time, we were talking about radicals, and we need to finish that bit up. So today's the 6th. And so, very quickly, to recap, the definition of radicals is, so let x and y be in the reals. So this is the definition of radicals. And let n be in the naturals with n more than 1. And so, naturals are non-negative integers, so 0, 1, 2, 3, 4, all those. And more than 1 means, well, we're starting at 2, so 2, 3, 4, etc. Then, so in the case, in many math definitions and in science where such things are used, very often when there is a natural involved, the result sort of splits into two categories, and that's the case here. We're going to have radicals that are even, that have the even behavior, and we'll have radicals that have the odd behavior. And I don't mean strange, I just mean, the parity is odd. So, in the left column, n is even, and in the right column, n is odd. So the following are equivalent in the left column. So y to exponent n is x, and then I'll write a blank. And 2, if you wanted to solve for y, then getting the caret n to switch sides, it switches sides like this. And then in the odd case, at least at first, it looks exactly the same. So y to n is x, and I'll leave myself a blank. And if we wanted to solve for y, then it would be y is nth root of x, like that. But this is not complete because we need to write something in that blank to make it correct. So in the even case, what do we have to write here? Yeah. Y is greater than or equal to 0. So, there's an and. So this and y is greater than 0. Okay? And here, there is no inequality. Which, in some sense, therefore I shouldn't have to write anything. But it's so notable that this is here and that this isn't. I'm literally writing that there's not anything here. Fine? So, as a result of those inequalities, I'm going to try, that looks a little washed out, I'm going to try to, nope. So is this better than it was before? Now you have a shadow. So do you like it this way or the other way? This way? All right, this way. Fine. So then this one, the even case, remember that this is like square roots. Like square root. And this one, the odd case, is like cube root. And one of the consequences of this inequality being here, and this being the even case, and no inequality here, and this being the odd case, is that over here we can say note that the input and output must be non-negative, and over here the input and the output can have any sign. Another consequence of this this parity stuff, parity, not parody, is that when you consider this, if you take an x and then raise it to exponent n, and then immediately after that compute nth root, so like that, then you get something, a particular result in the even case. And if you do the corresponding thing in the odd case, the result is different. So what do you get in the even case? Absolute value of x. And what do you get in the odd case? Regular old x. Okay, so that's a summary of all that. And then, okay, so let's do one more of those kind of exercises that we did last time. But this one will achieve like maximum difficulty, or whatever in this one. So one of the before I go on to the exercise, I want to point out that this theme where we're going to have an even case and an odd case, that's going to happen all throughout the semester. It's going to be everywhere. Okay, so then this is just the first time we're seeing it. Okay, another repeating theme in the class is that when we're doing exercises, very often, instead of selecting one from the textbook, what I'll do is I'll make an exercise right here in front of you so you can see exactly what I'm thinking when I'm making it. Because if you can understand how I'm making it, how I'm making a particular exercise, then you really know everything there is to know about that exercise. Okay, so to that end, this is a remark block. So now I'm going to write a hidden block. So hidden. So interpreting that, this is like me back in my office conspiring to make you an exercise. Okay, fine. So I want to ask you one of those radical questions, and because I want this to be basically the most difficult kind, I'm going to choose an even radical, so that the issue of absolute value comes up. I'm going to force that issue. So I'm going to choose n is 4, and again, this is me making the exercise. N is 4 because I want it to have an even one. So now I'm going to choose some variable to be in there, and p doesn't get used a lot, so I'll use p. And so now I want to have a bunch of p's inside of the radical. Now how many of them do I want? Well, if we're factoring things out of fourth root, then that means things come out in quadruplets, right? If we were doing cube roots, that'd be triplets. And if we were doing 27th root or whatever, then we'd 27 of them would come out at a time. Okay, so then suppose I want 3 groups to come out. How many p's do I need? I need 12, right? Because each group has size 4, and if I want 3 groups to come out, that means 12. Okay, so the group size is 4, and I want 3 groups to come out, so I'm going to have 12 p's. Okay, how about some q's? All right, so now that's the number of groups that came out. 3 groups come out are going to come out for the p's. Now I want some more. I want q's to come out. Now the group size is 4, but now I want an even number of groups to come out. So this is 3 groups would come out for the p's, but now I want some even number of groups to come out for the q's. So how about 6? Okay, that would mean that we'd get 6 of them to come out. And then just to make sure that stuff is lively, I'll say that that there's going to be some q's that are left in there that aren't going to be able to make it out. All right. So I'll do something like this. So this is equal to, plus 3 more. So that'd be 27, that'd be 24 and 3 more, that'd be 27. So that's how many q's I'm going to put in there. Fine. And then now I want some constant to be in there, so you got to deal with that complication too. Okay, so then now I'll take something nice here and write, how about 2 squared times 3. So I'll, again, this is me making the exercise. You're watching me do it. So I'll choose some small primes. So what are prime numbers, by the way?
Numbers that can be something by themselves.
Yeah. It's naturals whose only factors are 1 in themselves, right? So like 1 is, and the natural, it has to be more than 1. So 2 is prime, 3 is prime, 6 is not prime because that's 2 times 3. So I'll choose some small primes and then raise them to some small exponents. And then because this is because that's 4, I'll now raise this to exponent 4. And when I do that, I get 2 to exponent, distributing that'd be 2 to 8, and then multiplied by 3 to 4. And then to make sure that it's not perfect, I'm going to fiddle with it and say, well, I'm actually going to use 2 to 7, 3 to 4. That's what I'm actually going to use to sort of muddy the waters a little bit. And then now I'll type that into my calculator and get 2 to 7 times 3 to 4 is 10368. All right. So I'm making the exercise. And so now I'll write down the exercise. And this is hidden, right? You can't see it. So simplify by factoring out as much as possible. And it is the 4th root of 10368 multiplied by p. Well, I could write p to 12, but to muddy the waters even further, I'll break that up and say, well, here's 5 of the p's, and then I'll put the q's here. So then we have maybe I'll put like 20 of the q's here, and then another p here. So that's 6 p's accounted for, right? And now there's 6 more to go. So I'll put the rest of the q's here, and then the rest of the p's here. So 6 of them, 6 more. Okay. So, fine. Now, the first order of business, I'd say, is to look at that and say, well, I see some p's there, and then I see some more p's elsewhere. So there's some like trickery afoot. So the first thing is to make it, in my mind, is to simplify that much. So, all right, 4, and then that crazy number, 10368. And then how many p's are there? 12. Okay, 12. And then how many q's? 27. Okay, so that's good. Now, concerning that number 10368, we need to factor it. We need to figure out, what goes in there. So, I'll, this is something that you learned in, depending on your particular situation, around 7th or 8th grade or something like that. But that might have been a while. So 10368. Generally, the strategy is you just look at it and you just think, is there any small number that I can see definitely divides that? Well, how about 2, right? 2 definitely divides it. And then using my calculator, I guess, I could write 10368 divided by 2. That would mean I get what, 5184? 5184. So what I mean by that is that number is the product of those 2 numbers. And then now you just continue doing it. So like I can say, oh, there's another 2 in there, so I'll do that. 2592. And then, oh, look, there's another 2 in there. But, you know, by now I'm getting, you know, okay, how many 2's are going to be in there, right? So now I'm going to try and be more clever with my calculator and say, well, suppose I take 2592. I'm going to try to do it by 4. Does that work? That worked. I'm going to try to do it by 8. Oh, that worked. And then now I'm going to try to divide it by 16. Maybe that'll work. Ah, even that works. Okay, so maybe that's big enough, you know, for now. So then we can get a 16 to come out. And then when we do that, we get 162. So you want to do that because, you know, you want to try and make these big so that the whole process is small. If you just did it 1 2 at a time, it would one little 2 at a time. It would take a long time. Okay, so then 162, 162, divide by 2. Oops. Is 81. Oh, good. So what we're saying is that this number right here, the consequence of this is that it must be equal to 2 multiplied by 2 multiplied by 16 multiplied by 2 multiplied by 81. All right. So that's nice. That's nice. 16. That's 4 2's, right? That's 4 of them. So altogether, you know, how many 2's are there? There's 7, right? Because there's, you know, 1 2 3 2's like that, and then here's 4 more of them. So it's 2 to 7 times 81. And then, you know, we want to factor 81. Well, 81 is 9 times 9, and then each 9 is 3 times 3. Right? So then in terms of 3's, we could say that this is 2 to 7 multiplied by 3 to 4. Ah, we did it. Any question about this one? So now, do you observe that we recovered that much? You see it? It's much easier to make, in the same kind of way that it's easier to walk uphill than downhill. It's easier to make the problem than to solve it, usually. Okay, so that means that you know, we can write this like this: 4th root 2 to 7, 3 to 4, p to 12, q to 27. All right, things are as factored as they're going to get. Now that we've got the stuff in the radical as factored as much as we can, you look and say, okay, this is fourth root, 4th radical. So that means things come out in quadruplets. So let's start smuggling stuff out. So are there enough 2's to get out a group of 2's? Yeah, right, because there's 7 of them. And they come out in groups of size 4. So how many groups how many groups can we get to come out for the 2's? Just one group, right? And then there's going to be 3 that are left inside. Okay. So, you know, 2 to 4 is going to come out as just a regular old 2, and 2 to 3 stays inside. Okay, then how about 3 to 4? Do we have enough 3's to come out? How many of them come out? One group, right? And then how many are left inside? None, right? They all make it. Okay, so all the 3's escape. That's just a regular old 3. So there are no 3's. No 3's. That's a 3's. 3's. No 3's left inside. Okay, so then this would be 4th root. No, I just said I was taking stuff out. So then 2 made it out, 3 made it out, and then now we have the fourth root. And then concerning the 2's, there were 2 to 3 was left inside, all the 3's escaped, and then p squared q to 27. Any question about this step? All right. So then now we'll move on to the variables. So now again, we want to get p's to come out, and they come out in quadruplets. How many groups of quadruplets? How many sets of quadruplets can we get to come out concerning the p's? Three of them, right? And then how many p's will persist inside? None of them, right? So we're able to get all of them to come out. But here's the deal, is that because this is an even radical, we're smuggling p to 4 out of fourth root. So each one of the p to 4's comes out as what? Absolute value of p. Okay. So then we can get concerning that, you know, p to 4 is going to come out as absolute value of p, and it's going to do it 3 different times. The reason is because what we're doing is we're computing the fourth root of p to 4, which is absolute value of p. Okay, so then you know, you could say that this is 2 multiplied by 3 multiplied by, here's the first one that's the first group that snuck out, the second group that snuck out, the third group that snuck out, and then I'm leaving the q's for the next step. So that would be 2's. The 2's were all left inside. We got all the p's out, and the q's are still there, like so. Any question about this step? So now, under normal circumstances, when you're familiar with this exercise, typically you won't write absolute p, absolute p, absolute p like that, because, you know, that's why we have the exponent notation. Because, you know, x with exponent 5 means make 5 x's, x, 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 and multiply them all together. And there's nothing special about x. So there's, you know, here's an absolute p, an absolute p, an absolute p, and they're all multiplied together. What's the best way to write that? Absolute p cubed. So this would be 2 multiply 3 multiply absolute p cubed. Okay, good. And then fourth root. Here's all the 2's that were left, and here's all the q's that we haven't dealt with. Good. Now we want q's to come out again in groups of size 4. So how many groups of q can we get to come out? 6 of them, right? We can get 6 of them to come out, and then once 6 of them are out, six groups, that accounts for 24 of the q's. And then how many q's remain inside? 3 of them, right? So what I'm saying is that you know, is that if you take that number 27, then you could say that if we break this into groups of size 4, there'd be 6 such groups, and then there'd be 3 left over. Now, if that's bothering you, then you can sort of take the long way and say, well, I'll just take 4 at a time. So 4 come out as an absolute q. So write absolute q, and now there's 23. 4 more come out. Now there's another absolute q, and now there's 19 q's in there. You do it again, and then there's 15 q's. You do it again, and then there's 11, and then 7, and then 3. You just count up how many times you could do that. You could do it 6 times. So it would look like 2 times 3 times absolute p cubed. And then now let's see if we can do it in one step. I'll write absolute q, and then how many of them came out? 6. 6. And then fourth root of 2 cubed, and then there were 3 of these left over. 3 q's. All right. So any question about this? Now, notice that in the radical, there's a bunch of 2's in there. There's, you know, a bunch of them, and there's a bunch of q's in there. But, for example, concerning the q's, are there enough q's to get another group to come out? There aren't enough. So, we're not quite done with the exercise yet, but do you notice that, where did I put it? Oh yeah, right there. Do you notice that, we did what we said we were going to do? We said that, okay, I'm going to make an even problem so that the absolute value issue comes up. That happened. And then I said, okay, I want in the end, I want there to be 3 groups of p that came out. And then I wanted 6 groups of q to come out, and I wanted 3 to remain inside. And then here's the crazy number. Okay. So now, there's 2 kinds of simplification that are possible left. So the first one is that the instructions will probably say something like, concerning constants, multiply them out. So what I mean is, like, you need to say that's a 6, and you need to say that one's an 8. Okay, so that's easy enough to understand. But there's another issue here, and that is that concerning the absolute p cubed and the absolute q to 6, one of those can be simplified, but not the other. So here's the deal, is that absolute value of x to n, just for some x, this simplifies to just regular old x to n, meaning that you can drop the absolute value when what? When n is even. So, to be clear about that, I could say, well, how about, say, absolute value of -3 to 4? Well, the absolute value is going to flip that -3 to a 3, right? So that would be 3 to 4, like this, and that's 81. Suppose that instead of making those absolute values, I just make them parentheses like this. Then, the absolute value is not going to flip that to a 3 for us. But what this means is make 4 copies of -3. And so what I'd like for you to see is that we have 4 negative numbers all multiplied together. So the result is positive. Positive 81. Okay. So as a result, concerning these 2 things, which one can be simplified and which one cannot? Q can be simplified. The Q thingy, but not the P one. So you could write this as 6 multiply absolute P cubed multiplied by Q to 6, and then multiplied by 4th root of 8Q cubed. Like that. Any question about this one? So this is like maximum, for this kind of exercise, this is like the maximum difficult. Okay, so a couple comments I want to make is, when we were first talking about exponents and said, exponent is repeated multiply, and we had so many exercises where it was saying, write, no exponents, make it all the bit multiplies, and you had to write, a 6-inch wide expression of multiplies, or even like a grid of multiplies. Okay, so I hope that point is made, and it's not required for you to do that kind of thing anymore. Now, here's the problem, and the rub, kind of the issue, is that suppose that you don't write any work like this, so like that's not there, okay, and you don't write absolute q, absolute q, absolute q, absolute q, absolute q, absolute q. You don't have that step, so that you don't have a step like that one either. Okay, suppose that none of that's there, and you move from here to here, but instead of having the correct exponent like 6, you write something incorrect like 5. So now, first thing is that what you've written is not correct. So that's an issue. But the next issue is that it's not clear how that occurred. It's not clear to the grader how that occurred, why that occurred. So that's not like a minor issue. That's kind of getting on, medium big issue. Now, if you wrote this step, if you wrote absolute p, absolute p, absolute p, so that this step, is correct, and then you write one more step, and you put that one, and then instead of writing absolute p cubed, you wrote like absolute p, like to 2 or 4 or something like that, then now that's still a mistake, but now it looks like the problem isn't that you just really don't understand this at all. The problem is that you can't count. So that's less of a concern. You see what I'm saying? So if you if you refuse to write to show your work verbosely, then you're essentially denying the grader the chance of giving you the benefit of the doubt. Okay, because basically the instructions to the grader are, if it's not clear, then it's not right. And if it's not clear exactly how the manner in which the mistake was made, then it's a big mistake. Okay, fine. But I also want to point something else out, and that is that one of the comments that I receive a lot, one of the evaluation comments, because students evaluate the course and things like that, and some of my other colleagues have confirmed this, is that students say things like, well, the instructor always does easy questions in the lecture and then gives us really hard questions on the quiz, or something like that. That's, the same thing that I hear, that it's a different statement, but it's the same thing, is that students say, well, when you're doing it on the page and I'm watching you do it, it seems so obvious, and then when I go to do it, I can't make heads or tails of it, or something like that. So what I want to convince you is that those are really the same problem. It's the same issue. And here's what the issue is that I hope you've taken a little bit of anatomy and physiology. Like inside of our inside of our guts here, we've got like distinct units like a liver and kidneys and stuff like that, and it's real obvious. Like that part's definitely the kidney and that other part's definitely the liver, and it's not confusing. But if you look at a brain, it all just looks not everything is real clearly defined. Some things are clearly defined, but not all things. And here's the deal, is that there are in fact different parts of your brain, and some of them communicate extremely efficiently with each other because we're designed that way. Like the left and right hemispheres, we've got like a huge connection between them called the corpus callosum, very high bandwidth, very low latency, very fast. Fine, but when you're doing abstract thinking, that occurs here on the frontal cortex, in the top, right here, right above your forehead here, kind of forehead-ish. So when you're doing like abstract math thinking, like in your head, it's here. And our visual reasoning is primarily in our visual cortex, which is in the back, right here. And it's all part of your brain. If you just look at a brain, it'll just look like brain, But as it happens, the abstract part and the visual part are not connected so great. They're not. Okay, so then students say, oh, easy problems in here, hard problems on the quiz, or when I see the instructor do it, it looks so easy, and then I can't do it. Invariably, here's the issue, is that you're not putting your full mind to the problem because you're trying to keep it right here in this frontal cortex, and you're refusing to use your visual cortex. Now, how do you use your visual cortex? It's very simple. You take that thought that's in your mind, and then you need to put it somewhere you can see it. Right there on the page. And then once it's on the page, then it comes into your eyes, into your visual cortex, and now you've like doubled the amount of brain power that you can put to bear against the problem. Now, another way to say this is that here's a common thing that will happen in class, is someone will say, oh, I have a question. And then I'll say, okay, what's your question? And then it'll be a little bit vague. And I'll say, I'll give them a response and try and get them to say more. And then usually I'll go through that at least one more time, because very often, by the time the student is explaining like blah, 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 eventually there's a brief pause of like 3/4 of a second, and student says, never mind. All of that is that I'm purposefully doing something. I'm trying to get to your oral complex sound to get involved. And the process of making you say it is getting that other part of your brain involved, and then you say, never mind. Or when you come into office, I'll say, write it down. Can you tell me what problem you're having? Oh, I don't understand. You know, I'll understand what you're saying probably. I'll say, but I don't get it. You know, and then you write it down, and then oh, never mind. It's a very common theme. Now, I want to point out two things. Is that I think that teaching is very important. I think it's I like doing it. I think it's important for society, and I really take your time and my time seriously. And I've just spent 5 minutes talking about this. And I wasn't just like going off on a tangent. What I'm telling you is that this is something about the way you're made, and you might not realize it. So what I'm telling you is that when you refuse to show your work, you're doing two things. You're refusing to give the grader the opportunity of understanding that your error was a little error. You're refusing to give the grader the opportunity to give you partial credit. You're also refusing yourself the opportunity to use your full mind against the problem. Okay? Why does it, in the end, why does it look easy when I do it? Because I'm writing it all out. It's not any more complicated than that. The only complication is humans are all economical, which is a polite word to say lazy. Okay? And I'm not pointing the finger. I'm top lazy. I'm the top one. So like if I say that I'm top lazy, yet I'm doing it this way, then it must be because this is the laziest way I can possibly do it. I promise you. Good. Now that we can get past that. Fine. So now we need to define something new. Fractional exponents. So, the way that we've been dealing with this is we said, okay, x to 3 means make 3 copies of x and multiply them all together. And so that's fine. So we can deal with an exponent that's a positive integer. And even we can deal with negative integers because we can say y to negative 4. How do we handle y to negative 4? Right, the 1 over bit, right? Okay, so y to negative 4 is 1 divided by y to 4. Okay, so we can deal with positive integer exponents, negative integer exponents, but we can't deal with an exponent like 1.5. Because you try to insert 1.5 into that sentence we've been saying. X with exponent 1.5 would mean make 1.5 copies of x and then multiply them all together. What would it look like? 2 x's, x, x, 3 x's, x, x, x. Well, what would 1.5 x's look like? Now there's a problem, right? So you write just the one and not the other. I don't know. It doesn't work. So here's the rule. I can say let x be in the reals. Let 2 naturals now, m and n, be in the naturals. With n more than 1 and m and n have no common factors. Okay, so now that's kind of a complicated setup, so I want to make sure you understand why this is the setup. Is that here's the idea. Is that we want a simplified fraction m over n, like that. So if I write 3 over 2 like that, is that a simplified fraction? Yeah, because they share no common factors. So if you're saying no, then you might have been gotten a false hit on a different thing, which is to say a proper fraction. So a proper fraction is where the numerator is less than the denominator. Okay. So that's not what I'm asking about. I'm just asking, are there any common factors? Okay, so this one, yes. How about what's another fraction that has the same value as 3/2, but it's not simplified? 6 over 4. So not this kind. Okay. Then here's the definition. So one definition, definitions. So first is that when we write x with exponent 1 over n, so what this is talking about, this is like x to half, 1 over 2, right? X to 1/3, x to 1/7. So that means, by definition, is the nth root of x. So what I'm telling you is that these are the same thing. So you know what this is, and what I'm telling you is that this is just another way to say that. Now, because radicals have split on parity, that means that so does this. Has the exact same behavior. You know, so note the parity. Second is that x, so you know that's in parentheses there, and then x to m over n, like that. So this will allow us to do things like x to 3/2. So what it is, it's x to 1 over n, like that, and then raise that to exponent m. And of course, 1 over n, that means nth root, nth radical. So you could write this, if you like this. So what I want you to see from this definition is telling you that when you have x to a fraction, then in some sense you've got to deal with the denominator and you've got to deal with the numerator. You've got to deal with them both. And the way that you deal with them, you have to deal with them, this definition is saying you have to deal with them in a certain order. You have to deal with the denominator first. Okay? So denominator, i.e. the radical, first. Okay. So examples of this. So starting out with something simple, I could write 64 to half. And then writing this as the corresponding radical, this would be 2 radical 2 of 64, like that. And of course, under normal circumstances, you wouldn't write that 2, because square root is so important. It's the radical that doesn't need to say its name. And this is 8. All right. What about 2? How about negative 64 to exponent a fourth? What about it? Well, how do you write this as a radical? You know, so like this, right? It'd be 4th root of negative 64. Now, if it wasn't clear before, I hope that now looking at that, you have a quick moment of pause and say, oh, there's a negative in there. Is this one okay? No, right? Because this is an even radical. So the correct response to such a prompt is to say that this is not defined.
So you put it not defined and not try to separate it.
It is not permissible for you to do that. So this is an even radical, and it is not permitted for there to be negative inputs. How about this one? Negative 64 to exponent 1/3. How about that? Well, this would be cube root of negative 64. And again, you should have a moment's pause and think, oh, is that one okay? So is it okay? Yes. It is, because this is an odd one. So this is negative 4. All right. So then how about 27 raised to exponent 4/3? So this is the first time that our exponent has, its numerator has not been 1. So, the rule is that you have to deal with the denominator first. So according to the definition, this is, you could write this like this: 27 to a third, and then to a fourth, to 4, to exponent 4, like that. So what is 27 to exponent 1/3? 3. And then that's 81. So in this for this one, how about let's see, what time is it? So we're going to leave this off, and I'll do that on Wednesday, and then I need to say one more thing. So now here's a question. I want you to simplify it just like we were doing at the beginning of the so it's same request, but I'm going to warn you that there's a twist. Okay. So then cube root, I'll choose an odd one so that it's not too difficult. So cube root of, say, x to 5, so that'll be good, and then we'll also have like y to 7. Okay, so I want you to tell me how much, how we can simplify this. Okay, so now, if you're going to make an error, there's kind of, at this point in the course, I'd say there's kind of a high probability that you'll make an error. If you're going to make an error, you would have done it by now. You would have said, well, this looks like what we were doing before. It looks like I can get 3 of the x's to come out, right? And that's nice. And then I can get 3 of the y's and then 3 more. Well, that's not going to work at all. In fact, it is not possible to simplify this. So no simplification. No simplification possible. Now, to be clear about why this is the case, is that on the previous page, on the first pages there, we were doing something like this: cube root of x to 5 multiply y to 7. And so what's the distinction? The multiplication. Now, to be clear about why this is happening. So remember, So in this course, we said that add means exactly what you learned in Ms. Harris's class. Repeated add is multiply, and repeated multiply is what? Exponent. And we said that concerning this sequence of operations, there's a distribution rule for these two. There's a distribution rule for those two. But one of the most common categories of errors is students trying to say that there's a distribution rule for these two. There isn't. So now, the punchline is now I'll write this in an overly pedantic way. So I could say in the first place, that's x to 5 plus y to 7 with exponent 1/3, right? And then to be really over the top, instead of writing superscript, I'll write it with caret. Can you see that they don't mix? Whereas these do, right? Caret multiply, good. Caret add, no good. All right, have a nice Wednesday. Please turn in